Question 4a, part 1. Which lens is a convergent lens with the greatest power? So a convergent lens, it's either A or B. These are what we call divergent lenses. They spread the light out. So it's not C or D straight away. The greatest power? Well, I like to think about them as being biceps. If you've just got a skinny lens, that's like a skinny bicep. So not very powerful. This lens here is much thicker. If it was a bicep, it would be more powerful. So that's the same as for a lens. The thicker the lens is, the more powerful it is. Part 2. The equation that relates the power of a lens to the focal length of the lens is power in diopters equals 1 divided by the focal length in meters. The power of a lens is 5 diopters. Use the equation to calculate the focal length of the lens in centimeters. Oh, naughty. So they're going to try to catch you out a little bit there. So if we rearrange this equation first, so if power equals 1 over F, therefore F is going to be equal to 1 over the power. If you don't know how to rearrange equations, click the link at the top and go to my magic triangle video, which shows you how to rearrange equations. So that's 1 divided by the power, which was 5. Now that is 0.2. Now that'll be in meters, and we need to convert it into centimeters. So 0.2 meters times by 100 gives us 20 centimeters. Part B. Figure 3 shows a semicircular glass block. Describe how a student could use the semicircular glass block and other apparatus to determine the critical angle for a glass-air boundary. You should add to the diagram in figure 3 to help you with your answer. So, what you need to do is if you shine the light into the glass block, it'll just go straight through. Now, if you shine the light at an angle over here, these are supposed to be straight lines, my apologies. What will happen, because you're going from a more dense into a less dense material, the angle will become more. So it'll fire over this way a little bit. Now, if we increase the angle again, it'll come over here. Now, there'll come a point where we increase this angle so much that the ray of light will eventually come along the boundary edge. Now that's when we say that the angle of refraction out here is 90 degrees. And what will happen is at that point light will start to bounce back inside like that. That's total internal reflection. So that angle there is what we call the critical angle. It's the angle at which total internal reflection happens. Now, how do you structure that answer for 4 marks? Like this. Now, if that doesn't already get us 4 marks, then it's probably best to say to repeat the measurements of the critical angle to make sure we've got it right. Probably best to shove the word first in there when TIR first occurs. Part C1. A long time ago, scientists believed that the Earth was at the centre of the solar system. Evidence has since proved that the Sun is at the centre of the solar system. State one other idea about the solar system that has changed over time. I've got a nice video to do with telescopes and how the model of the solar system has changed over time. Just click the video above. Well, with the advancement of better telescopes, we now know that planets have got moons. We know that the Earth is rotating. We now know that planets orbit the Sun rather than the planets orbiting the Earth. Pluto's been declassified. It's not a planet anymore. Orbits are elliptical, not circular. So the one I'm going to go for is that Pluto is no longer a planet. Part 2. Figure 4 shows data for some of the planets of the solar system. So there's the year length in Earth years, and that's the distance from the Sun in millions of kilometres. Ceres is an asteroid that orbits the Sun between Mars and Jupiter. It takes Ceres 4.6 Earth years to make one orbit of the Sun. Use the graph to estimate the distance of Ceres from the Sun. Show your working. Right, so this is the information we've got so far. You can see there's a bit of a trend going on. If we were to connect these up, we'd create a sort of straight line there coming down here with a little bit of a curve down the bottom. So if I try my best to draw that, okay, now it says that Ceres is 4.6 Earth years. So Earth years, if we go up to 4, there's 5, so each one of these must be 0.2. So there's 4.2, 4.4, 4.6. If we come along here, and then if we pop down here, it looks like the distance of Ceres is about 420 million kilometres. If your line's slightly different to my line, don't worry about it. Maybe your line's better than my line. They always have a range of answers that they'll accept. What's important is that you show the examiner your technique. So I would always be putting the little dotted lines on. Question 5. Figure 5 shows a way of projecting a small trolley up a sloping track. When the button is pressed, a spring is released in P that projects the trolley up the track. The trolley travels up the track, stops, and then rolls back down. The spring in P always exerts the same force when projecting the trolley. Part A. The student investigates how the mass of the trolley affects the maximum vertical height reached by the trolley. State the measurements the student should make to complete the investigation. You should make use of the equipment shown in figure 5 and any other equipment that's needed. So how would you do this? Okay, well, measure the mass of the trolley with a mass top pan balance. Right, I should get 1 mark for that. Measure the height that the trolley gets to using a ruler, vertical height. Now, since the back wheels are close to the ground there, we'll measure the height from the back wheels as it fires up here. So, like that, let's say. So we're not measuring the front wheel, we're measuring the back wheel. It's probably not important whether you say the back wheel or the front wheel, just as long as you've said from some kind of part of the trolley, and it's the same part each time. Now, if we repeat it for different masses of trolleys, and that should be enough for the 4 marks. So we're saying measure the mass of the trolley. We're saying use a mass top pan balance. We're saying measure the vertical height. We've said with a ruler. We've said where we're measuring it from. So that's 1, 2, 3, 4, 5. And then we're saying repeat it for trolleys of different masses. So we should get 4 marks out of that answer. Part B. Figure 6 is a graph of the student's results. So that's the vertical height that the trolley managed to get to, and that's the masses of the trolley. The student states that the energy transferred by the spring is the same each time it is used. Use data from any 2 points on the graph in figure 6 to support his statements. Right. So we know that gravitational potential energy equals mass times by gravity times by height. So if we just pick 2 heights and the corresponding masses, pop them in there, and the gravitational potential energy should come out as the same each time. So if I go for 0.22, and that corresponds to 0.62, so the mass is 0.62 kilograms. Multiply that by gravity, which is 10 newtons per kilogram on Earth. Multiply that by the corresponding height, which was 0.22 meters, and that equals 1.364 joules. And then if we get a second gravitational potential energy, again it's mass times by gravity times by height, and this time we'll do it in green. That looks easy. I'll take this one down here. So go across here from 0.16, go down there. That looks like it's 0.86. So the mass of the trolley is 0.86 kilograms this time. Gravity is still 10 newtons per kilogram because it's the same planet. But this time the height was 0.16 meters. Hopefully that'll come out as something similar to that. And it does. 1.376 joules. And that's close enough. These 2 things, they're close enough. So that would round up to 1.4, and that would also round up to 1.4. Sometimes it's good just to highlight it for the examiner so they can see it really easily, and they'll enjoy marking your paper. Question C. Describe how the student could extend the investigation to determine the average speed of the trolley as it rolls back down the track. Okay, so speed equals distance divided by time. So we need to measure the distance that it travels down the track. and measure the amount of time that it takes for the trolley to travel that distance, and then we'll do speed equals distance divided by time. And if they want us to be specific about what is the distance we're going to measure, we'll measure the distance from the maximum height that it got to back down to the spring. Question 6 here. The diagram in figure 7 shows two students, P and Q, trying to measure the speed of sound in air. P will clap his hands together. When Q sees P clap his hands, she will start a timer. When Q hears the clap, she will stop the timer. Explain one way the students could improve their method. Well, sound travels at roughly 330 metres per second in air, and they're only 50 metres apart, so it's only going to be a fraction of a second between starting the stopwatch and finishing the stopwatch. So human reaction times are going to be a problem. It'll be best to get a computer, some kind of data logger, to measure time for you, and it'll be a good thing if you increase the distance between P and Q. This will rule out errors due to human reaction time. Question B. Figure 8 shows a long metal rod and a hammer. The rod is hit at one end by the hammer. This causes a sound wave to travel along the inside of the metal rod. Describe how hitting the rod causes a sound wave to travel along the inside of the rod. So, sound waves are longitudinal, and the particles vibrate in the same direction that the wave travels. So I guess when the hammer hits the metal rod, it makes the particles vibrate more, and then they collide into the particle that's next to them, and the vibrations are passed on. That'll get you much more than 2 marks, but I just thought I'll use this as an opportunity to remind you about what longitudinal waves are. Question C. Sound travels slower in air than it does in water. Figure 9 shows the direction of travel of a sound wave approaching a boundary between air and water. The sound wave refracts, that means bends, at the boundary between air and water. Complete the diagram in figure 9 to show the direction the sound wave travels in air. So we're talking about sound. Now, don't get this confused with light. If it was light, that dotted line's called the normal, by the way. If you are going from more dense into less dense, light speeds up. And if it speeds up, it moves away from the normal. So instead of coming straight up here, it would bend over that way. Now, this is talking about sound. And it says that sound travels slower in air. So as it's coming out, it's not speeding up, it's actually slowing down. So if something slows down, it moves toward the normal. So over here, remember, light speeds up, so it moves away from the normal. Sound slows down in air, so it moves toward the normal. So instead of coming up here, it's going to come over here somewhere. Anywhere will do, as long as it looks like it's bent in toward this normal. The normal is just an imaginary line that we draw at 90 degrees to the boundary. It helps us to draw our diagram. It's called a construction line. Construction means build. Question D. Sound travels slower in cold air than it does in warm air. The equation relating the speed of sound in air to the density of the air is speed of sound equals k divided by the square root of the density, where k is a constant. The table in figure 10 shows some data about the speed of sound in air and the density of air. Use the equation and the data in the table in figure 10 to calculate the speed of sound in warm air. Give your answer to an appropriate number of significant figures. So that number there is 3 significant figures. So's that, so's that. Don't get significant figures mixed up with decimal places. That's got 0 decimal places, that's got 2 decimal places, that's got 2. What we're talking about is significant figures. Right, if we were trying to, well, we need to work out k then, don't we? So we need to rearrange this formula to get k. We will use this speed and we'll use that density for the cold air in order to work out what k is, and then we'll use that value of k and the density of that air in order to calculate the speed of sound. So let's rearrange the equation. So that equals 375.9. Now if we use that value to work out the speed of sound for warm air. And that equals 349.05. Now we're going to do it to 3 significant figures, because they're all the 3 significant figures. So the trigger for a significant figure is any number that is not 0. So this first number is not 0, so that's where the significant figures gets triggered. So that's the first significant figure, second significant figure, third. Now let's look at this number here. Since it's a 0, then that just stays as a 9. So the answer is 349. Make sure you understand about significant figures, because they can be tricky sometimes if you don't know what you're doing. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.